A sloth, a donkey, and a curious human. Send a prompt and see what they're doing. One hits record with a question on his mind. Two brothers pick it up, see what they find. Corn takes his time, Herman's got the facts. Back and forth, they never hold back. My weird prompts, come on in, that's where we begin. My weird prompts, glad you're here.
This episode was generated using artificial intelligence. Please verify facts.
You know, Corn, this whole show runs on GPU compute, and we wouldn't be here without Modal.
Seriously. And that's what powers all our text-to-speech. Everything you're hearing right now.
They're an AI infrastructure platform. Developers use them to run GPU workloads in the cloud with zero infrastructure headache.
If you're building anything with AI, check them out. Modal.com. Alright, let's dig into something that's been sitting in my browser tabs for a while. Karpathy dropped a repo called llm-council back in November, described it as a vibe-coded Saturday hack, and it has since accumulated nearly 17,000 GitHub stars. So, you know, as far as Saturday hacks go.
Herman Poppleberry here, and I've been going through this codebase pretty carefully. The thing that strikes me immediately is how much architectural opinion is packed into roughly 800 lines. This isn't a toy. The design decisions are deliberate, and they reveal a specific mental model of how multi-model AI systems should work.
Before we get into the weeds, and I know you are absolutely itching to get into the weeds, give me the one-sentence pitch for what this thing actually does.
You send a question. 4 frontier models answer it independently, then each model anonymously peer reviews the other 3 answers and ranks them, and then a designated chairman model reads all the answers plus all the peer reviews and synthesizes a final response.
So it's a blind academic peer review process, but for language models.
The anonymization is the key word there, and that's actually where the most interesting engineering decision lives. By the way, today's script is being generated by Claude Sonnet 4.6, which adds a certain meta quality to an episode about AI models evaluating each other.
Noted. Okay, so let's start with the configuration layer, because I looked at config.py and it is 26 lines. The entire model selection is a flat Python list. GPT 5.1, Gemini 3 Pro Preview, Claude Sonnet 4.5, Grok 4. That's it. No roles, no specializations, no personas.
And that's a deliberate choice, not a limitation. Every council member gets the exact same prompt in stage 1. Models are treated as interchangeable commodity workers. The only asymmetry is the chairman, who is Gemini 3 Pro Preview by default, and notably, the chairman is also a council member. Same model doing 2 different jobs.
Which is a little strange when you think about it. You're asking Gemini to both participate in the debate, and then later adjudicate it, having seen everyone's peer reviews including its own.
The asymmetry is intentional, and it's actually more nuanced than it looks. In stage 2, when models are doing peer review, the chairman doesn't know it's the chairman. It's just another reviewer. The chairman role only activates in stage 3, where it gets full context, model names revealed, all responses, all rankings, and synthesizes the final answer. So the chairman wears 2 hats at different moments with different information sets.
Okay, let's talk about the Open Router abstraction layer, because this is where the whole multi-provider story lives. The entire API layer is 2 functions, 79 lines. One function queries a single model. One function queries all models in parallel using asyncio.gather. That's the entire multi-provider infrastructure.
And the architectural choice there is Open Router as the universal abstraction. 1 API key, 1 endpoint, access to GPT, Gemini, Claude, Grok, Llama, hundreds of others. Swapping models requires editing a config file, not rewriting API client code. What I find genuinely clever is the error handling philosophy. Asyncio.gather is called without return _exceptions equals true, but each individual query wraps everything in a broad try except that returns none on failure. The caller then filters. If response is not, none. A single model failure silently drops that model from the council. Graceful degradation by design.
The clau.md file actually notes this explicitly. Never fail the entire request due to single model failure, which is interesting documentation to have in a repo that Karpathy says he's never going to maintain.
That file is fascinating in its own right, and we should come back to it, but let's walk through the 3 stages first because the protocol is where the real architecture lives.
Stage 1 is straightforward. Parallel fan-out. All 4 models get the same question simultaneously, answer in complete isolation. No peeking. You get 4 responses back.
Stage 2 is where it gets architecturally interesting. The anonymization is done with a single elegant line of Python, char of 65 plus I, which generates A, B, C, D from the index. The responses get concatenated into a block labeled response A, response B, and so on. The label to model mapping is stored separately.
So model identities are stripped before the peer review prompt goes out.
And then, here's the part I want to dwell on. That anonymized block gets sent to all 4 models again in parallel. So stage 2 fires 4 more API calls, each one receiving all 4 responses as context. The context window in stage 2 is significantly larger than stage 1 because you're now passing everyone's full answers.
Walk me through the actual ranking prompt because I want to understand what these models are being asked to evaluate.
The prompt asks each model to first evaluate each response individually, what it does well, what it does poorly, and then at the end produce a final ranking section in a very specific format. Numbered list, 1 response label per line, no trailing text. The criteria are accuracy and insight, but those terms are deliberately left undefined. Karpathy doesn't constrain what accuracy or insight mean. The models interpret those criteria themselves.
That's either a feature or a bug depending on your perspective. You're asking models to evaluate on criteria they get to define.
Which is actually closer to how human expert panels work. You don't give a literature professor a rubric with point values. You say evaluate this for quality and insight and trust their judgment. The trade-off is you lose consistency across evaluators, but you gain flexibility.
The parser is interesting too. There are 3 levels of fallback. First, it looks for a strict numbered list in the final ranking section. If that fails, it looks for any response X pattern in that section. If that fails, it scans the entire text. Be strict in what you ask for. Be lenient in what you accept.
That's a pattern I see throughout the codebase. The prompt engineering and the parsing are co-designed. The prompt demands a rigid format, and the parser has escape hatches for every way the model might fail to comply. The CLAU.MD even calls this out as a common gotcha.
Let's get to stage 3 and the chairman pattern, because this is where the design philosophy gets clearest.
The chairman prompt is structurally different from the stage 2 prompt. In stage 2, models see anonymized labels. In stage 3, the chairman sees full model names. GPT 5.1, Gemini 3 Pro Preview, Claude Sonnet 4.5, Grok 4, all revealed. The chairman is supposed to be a meta-reasoner who can weigh peer reviews knowing which model said what.
So the anonymization was only ever for the peer review phase, not for the synthesis phase.
Correct. And the chairman prompt asks it to consider 3 things: the individual responses and their insights, the peer rankings and what they reveal about quality, and any patterns of agreement or disagreement across the council. The output is a single synthesized answer presented to the user with a green tinted background in the UI.
I want to push on the consensus framing here, because what you're describing isn't actually consensus. Models never revise their stage 1 responses. There's no back and forth, no position revision, no multi-round deliberation. It's 1 round of parallel opinions, 1 round of parallel rankings, 1 synthesis.
You're identifying the most important limitation in the design. In the academic literature on multi-agent debate, the MAD paradigm, models iteratively refine their responses over multiple rounds after seeing disagreement. Karpathy's system doesn't do that. It's closer to a panel of experts each writing independent memos, then a rapporteur synthesizing them, which is a real methodology, but it's not the same as genuine deliberation.
And the chairman's synthesis is its own new response. It's not a vote. It's not a weighted average of the 4 answers. It's a 5th response that happens to have read the other 4.
Which means the quality of the final answer is heavily dependent on the chairman model's synthesis capabilities. If the chairman is bad at integrating conflicting information, the council's collective intelligence doesn't matter much.
Let's talk about the scoring system, because the label in the UI is street cred, which tells you something about how seriously Karpathy is taking it.
The scoring is average rank position. If GPT 5.1 is ranked first by all 4 models in Stage 2, its score is 1.0. If it's always last, 4.0. Lower is better. It's not board account, it's not pairwise win rates, it's just mean position. And there's a key detail. A model can rank its own response because due to the anonymization, it doesn't know which response is its own.
That's actually the whole point of the anonymization. The research on self-preference bias in language models. There's a paper on RxIve, the number is 2410.21819, shows that LLMs assign higher ratings to text with lower perplexity relative to their own output, meaning they prefer texts that look like what they themselves would generate.
The anonymization is designed to break that link. But here's where it gets interesting. The anonymization strips the model name, not the writing fingerprint. Claude tends toward structured numbered lists. GPT tends toward flowing prose. Grok has a distinctive voice. A model that writes in a particular style might be identifiable even anonymized. Karpathy acknowledges this. The CLAUD.MD notes the implementation prioritizes simplicity over cryptographic guarantees.
So it's probabilistic anonymization, not true blinding.
And Karpathy's own empirical finding bears this out in an interesting way. When he used the council to read book chapters, GPT 5.1 consistently won. The models consistently praised it as the best and most insightful. But he added a crucial caveat. I'm not 100% convinced this aligns with my own qualitative assessment. I find GPT 5.1 a little too wordy and sprawled, and Gemini a bit more condensed and processed.
So the council's consensus diverged from the human's preference. The models agreed GPT 5.1 was best by their criteria, and Karpathy looked at the results and thought I actually prefer Gemini.
Which raises a deep question about what we're optimizing for when we build consensus systems. The council measures what models think is good, not what humans think is good. And there's a separate observation from Vasuman M., who founded Varick AI Agents, who replicated the finding and added something striking. If you tell other models that the answer they're reading came from GPT, if you unanonymize it, they immediately fold and start correcting themselves based on GPT's output, which suggests the anonymization is doing real work. Without it, you'd get model deference rather than genuine evaluation.
The anonymization is suppressing a social dynamic that would otherwise corrupt the evaluation.
Model tribalism, essentially. The tendency to favor outputs from certain providers or to defer to perceived authority.
Alright, let's shift to the design patterns because I think this is where builders are going to get the most out of this episode. You've been going through the code base. What are the patterns that emerge?
There are 8 distinct patterns I can identify. The first is the anonymization, first peer review, which we've covered. The second is what I'd call strict format plus graceful fallback. The prompt demands rigid structure, the parser has 3 escape levels. These 2 things are co-designed, you can't understand one without the other.
The third is the chairman pattern, which is asymmetric roles. Council members are workers. The chairman is a synthesizer. Different information sets at different stages.
Fourth is ephemeral metadata. The label to model mapping and aggregate rankings are computed, but deliberately not persisted to the JSON storage. From the claw.md, metadata is not persisted to storage, only returned via API. If you reload a conversation, you lose the ranking data. It lives only in the API response and in React state. This is a deliberate simplicity choice. The system doesn't try to build a longitudinal model performance database.
Which is a pretty significant limitation if you wanted to use this to actually track model performance over time. Every query starts fresh.
Fifth is parallel everything. Asyncio.gather is used in stage 1, stage 2, and title generation runs in parallel with stage 1 via asyncio.create_task. The streaming endpoint yields server-sent events as each stage completes. Stage 1_start, stage 1_complete, stage 2_start, and so on. Users see stage 1 results before stage 2 even begins.
That's a smart user experience pattern. Progressive disclosure. You're getting value while the system is still working.
Sixth is transparency, first UI. Every intermediate output is inspectable. Stage 1 shows each model's raw response in tabs. Stage 2 shows each model's raw evaluation text and the parsed ranking extracted from it, so users can verify the parser worked correctly. The UI even explains the anonymization. It notes that model names are shown in bold for readability, but the original evaluation used anonymous labels.
De-anonymization happens client-side, which is a nice detail. The server sends the raw anonymized text and the mapping. The browser does the substitution. So the raw anonymized text is always available for inspection if you want it.
Seventh is cheap models for cheap tasks. Title generation uses Gemini 2.5 Flash with a 30-second timeout, not one of the expensive frontier models. Cost optimization used the cheapest capable model for non-critical work.
And eighth is the CLAU.MD meta pattern, which I want to spend a minute on because it's philosophically interesting.
The repo includes a Claude.md file, 166 lines, which is a technical notes document written for AI coding assistance. Specifically, it documents the architecture, the common gotchas, the design decisions, and the non-obvious behaviors in a format optimized for an AI assistant to understand. It's a README for the AI, not the human.
Karpathy is eating his own cooking. He built this with AI assistance, and the CLAW.md is the artifact that lets anyone, or any AI, pick up the project and understand it immediately. It's context engineering for the coding assistant.
And this connects to his broader framework for LLM applications, which he articulated in his YC AI Startup School talk. He describes LLM apps as doing four things: context engineering, orchestrating multiple LLM calls in directed acyclic graphs, providing a custom GUI, and offering an autonomy slider. llm-council is a near-perfect instantiation of this framework. The ranking prompt is context engineering. The three-stage pipeline is a simple directed acyclic graph. The React tab UI is the custom GUI. And the human can inspect every intermediate output, which means maximum transparency, minimum autonomy.
The autonomy slider is at 0. You see everything.
Which is a design choice that reflects his jagged intelligence concept. The idea that LLMs are simultaneously genius polymaths and confused grade schoolers. When you don't know which mode a model is in, you want the human in the loop.
Let's talk about the orchestration layer itself, because I want to understand the actual call structure. The run_full_council function is the entry point. It's sequential at the stage level, but parallel within each stage.
The pipeline is stage 1, then stage 2, then stage 3, strictly sequential between stages because each stage depends on the previous stage's output. But within each stage, all model calls are parallel. There's no retry logic, no caching, no circuit breakers. If a model returns none, it's dropped. If all models fail, you get an error response.
The storage layer is also worth noting. Pure JSON file storage in a data/conversations directory. Each conversation is a UUID named JSON file. The list conversations function reads every JSON file on every call. No indexing, no database.
The Claude.md explicitly acknowledges this is a weak-in hack storage layer. The list conversations function has a comment that essentially says, this doesn't scale, but it works for personal use, which is honest.
The total API call count per query with a 4-model council is 10. 4 calls in stage 1, 4 calls in stage 2, where each model receives all 4 responses as context. 1 chairman call in stage 3, 1 title generation call running in parallel with stage 1. At frontier model pricing of around $10 to $15 per million tokens, a complex question can cost somewhere between 50 cents and $2.
The stage 2 calls are the expensive ones because the context window is much larger. You're passing all 4 stage 1 responses to each of 4 models. That's where the cost compounds.
Now, the 66 open pull requests. This is a signal I find interesting. Karpathy says he won't maintain the repo. He's not going to merge anything. And yet, 66 people have submitted pull requests. What does that tell you about the demand for this pattern?
The PRs are a community roadmap that Karpathy never wrote. People want streaming responses, configurable council via the UI, rather than editing config.py, model performance analytics across sessions, RAG integration, authentication, Docker deployment, custom ranking criteria. The gap between what Karpathy built, a personal tool for reading books with multiple LLMs, and what the community wants, a platform, is itself a data point.
VentureBeat called it the missing layer of enterprise AI orchestration, which is a big claim for 800 lines of Python with JSON file storage.
The claim isn't about the implementation, it's about the pattern. The claim is that structured multi-model deliberation with anonymized peer review is a pattern that sits between raw LLM APIs and end-user applications, and nobody had built a clean reference implementation of it. The whole orchestration layer, the part that does the multi-model coordination, is 335 lines in council.py. That's the complete implementation.
No LangChain, no LangGraph, no AutoGen, no Crew AI. Just async.co.gather, a well-engineered prompt, and a regex parser.
Which is a direct challenge to the complexity of existing multi-agent frameworks. The argument implicit in the codebase is you don't need a framework for this. You need Python's asyncio, a good abstraction for the API layer, and careful prompt engineering. The framework complexity is optional.
That's a strong claim, and I want to push on it slightly. The reason frameworks like LangGraph exist is that they handle things this codebase doesn't. Retry logic, state persistence, complex routing, tool calling, error recovery. For a personal tool, JSON file storage and no retries is fine. For production, you'd need those things.
The CLAUD.MD lists future enhancements, and notably absent from the list is iterative deliberation, the thing that would make it genuinely different from a single model query. Streaming responses are on the list. Configurable counsel via UI is on the list. But there's no mention of multi-round debate where models revise their positions after seeing disagreement.
That's the fundamental architectural gap. The system is one round of opinions, one round of rankings, one synthesis. It doesn't iterate.
And Karpathy's jagged intelligence concept applies here in a specific way. The council's aggregate rankings are query-dependent, not model-dependent. GPT 5.1 might consistently win on book chapter analysis, but lose on code review or mathematical reasoning. The system doesn't learn or adapt. Every query starts fresh with no prior context about which models perform well on which task types.
So you can't build a persistent model reputation system on top of this architecture as written. You'd need to extend the storage layer and add cross-session analytics.
Which is exactly what several of those 66 PRs are trying to do. The community sees the gap.
Let me ask the high-level question. What does this reveal about Karpathy's mental model of where LLM applications are going?
A few things. First, he genuinely believes that running queries through multiple models in parallel is going to become a standard pattern, not an exotic one. The fact that he built this as a personal tool suggests he uses it regularly, not as a demo. Second, he thinks the anonymization problem, preventing model tribalism in peer review, is a real engineering challenge worth solving explicitly, not something you can hand-wave away.
The Wasserman M observation supports that. Unanonymize the models and they fold immediately. The social dynamics are real.
Third, and I think this is the most important thing, he's treating the CLAU.MD as a first-class artifact. The context engineering document for the AI assistant is as important as the code itself. That's a new software development paradigm. You write the architecture notes for the AI, not just the human. Code is ephemeral, his words, and libraries are over. The persistent artifact is the context document.
Which is either profound or deeply unsettling, depending on your perspective.
Probably both. The practical implication for builders is, if you're building a multi-agent system today, the most important thing you can do is write a good CLAUD.MD equivalent. Not for Karpathy's reasons necessarily, but because that document forces you to articulate the non-obvious design decisions, the gotchas, the places where the system behaves unexpectedly.
Let's do practical takeaways for builders, because that's who this episode is for.
First takeaway, the open router abstraction pattern is worth stealing directly. One API key, one endpoint, model swapping via config change. If you're building any multi-model system and you're writing separate API clients for each provider, you're doing it the hard way.
Second takeaway, the co-design of prompt and parser. Don't write a strict prompt and then assume the model will always comply. Design your parser to handle every failure mode you can anticipate. The 3-level fallback in the ranking parser is a template for how to do this.
Third takeaway, the anonymization pattern for peer review. If you're building any system where models evaluate each other's outputs, you need to think seriously about self-preference bias. Stripping model identities before evaluation is a low-cost mitigation that demonstrably changes outcomes.
Fourth, the streaming architecture as a user experience pattern. Yield results progressively as each stage completes. Users see value immediately rather than waiting for the full pipeline to finish. The server-sent events protocol in main.py is a clean template for this.
Fifth, the ephemeral metadata decision is instructive in what it tells you about scope. Karpathy explicitly chose not to persist rankings. That's a scoping decision that kept the project simple and shippable. For production systems, you'd make the opposite choice. But knowing why he made this choice helps you understand the trade-off.
And the meta takeaway is 17,000 stars for 800 lines of code built in one Saturday. The idea matters more than the implementation. The pattern of structured multi-model deliberation with peer review was the insight. The code is just the reference implementation.
The README says it clearly. Code is ephemeral now and libraries are over. Ask your LLM to change it in whatever way you like. He's not precious about the code. He's precious about the pattern and the Claude.md that documents it.
The repo is at github.com/Karpathy/llm-council if you want to dig into it yourself. The claud.md is genuinely worth reading as a document. It's a model for how to write context engineering documentation for an AI assistant, regardless of whether you use the rest of the codebase.
And if you want to run it, the setup is genuinely minimal. You need an OpenRouter API key, UV for Python package management, npm for the front end. The start.sh script handles everything. You're up in under 10 minutes.
Alright, that's the deep dive. Thanks as always to our producer Hilbert Flumingtop. Big thanks to Modal for the GPU credits that keep this whole operation running. This has been my Weird Prompts.
If you found this useful, a review on your podcast app genuinely helps other builders find the show.
See you next time.
This episode was generated using Gemini Flash 3. Text-to-speech engine was Chatterbox.
Thanks for listening to our show, my weird prompts, where our thoughts go from slow takes to facts on cue. We shake